Oops, not this one.
Thank you. So I'll go over the paper that we proposed on hierarchical reinforcement learning. On hierarchical heterogeneous multi-agent reinforcement learning for a classical problem on coordinated box pushing. So this is a proposal to like a work we're conducting, and so we're kind of like formulating and looking at this classic problem from a multi-agent reinforcement learning perspective. The application could be used in multiple cases, and we're trying to see how agents can coordinate, and then trying to set up the scenario where we have a box of different sizes, and then using this agent, trying to push these boxes. And so, and then in the MARL scenarios, there are different architecture that are already proposed. And so there was this paper that looked at this problem and proposed that IPPO performed better than the other because, for example, for a multi-agent PPO, the action space is usually large. And so for the agent to kind of like find the box and then push it would become a harder problem. And so they proposed, they solved it with IPPO, and they showed that IPPO can perform better. And so with this intuition, we're trying to look into like how we can also incorporate with heterogeneous agents and then see how that works. So we're looking at, suppose, say, physical heterogeneity where you have some agents that are differentially driven or some agents that are quadrupod, and we're trying to look at first from the fully observable, and then we're trying to narrow it down to a decentralized POMDP. And so recently there was an architecture that was proposed to solve this problem with a hierarchical architecture. The idea is that the reinforcement learning or the multi-agent reinforcement learning doesn't have to solve the whole thing. And so we can break it down and solve it with this hierarchical approach where for example, in order to get to the box, we can use a planning algorithm, whereas the agents can adjust their body. For example, in this case, it's quadrupod, adjust their body to kind of align and then push the box. And so they proposed this architecture, and we're trying to build off of this in a way that we can, again, incorporate heterogeneity and try to solve this problem. For the scenarios that we're looking at is this preliminary steps that we have. And we have two agents. This is homogeneous, but in the future work, we're trying to replace this with like heterogeneous agent and try to solve this problem. So this is again at initial stage, and we're trying to set up the problem statement and try to solve this. And we can talk about it in the poster session later. Thank you.
Number 8. The second is the video. The presenter.
Hello, good morning. Hey, everybody. My name is MADSEBali, and I will be discussing about our research digital twin synchronization for real-time process control using CMASDL in smart additive manufacturing. And the digital twin framework that we have made established was using the Viper robot arm, so Viper X300S robot arm. We first set up the environment in Unity, and we also added ML agents and ROS TCP server for ML agents for reinforcement learning and ROS TCP server for the connection. But however, even the ROS TCP server was not enough because we need to make a ROS to message package such that Unity could make a message and send it into the ROS TCP server. And then we needed to make a ROS2 package so that we can download that specific message into ROS and then finally manipulate the robot arm. So for the reinforcement learning training, we used software critic through ML agents. And on the right side, we can see the environment with the consist of the robot arm, the cube object, and the goal. The robot arm's end effector also has a box trigger, which is an area in which if the cube object enters or touches the boundary, it will the unity will understand or this environment or this interaction as a touching. So that's how it understands touch. So for the first case, we will make the robot agent reach and touch the cube object. And for the second case, we use the first case's trained parameters, network parameters, to initialize second case. The task is mainly for pushing the cube object into the goal. So the virtual environment maintains the properties and characteristics of the real robot or real environment, so that the virtual environment robot arm is restricted. It does not go randomly anywhere. It has to maintain it has to move within its restricted joints, and thus it is safe and flexible and scalable and to do complex tasks in the Unity environment and then transfer it to the real robot. The results for case one, that is target reaching and touching. So in this case, if the box trigger and the cube object collides for the touches, the episode will end. And that's why it is quickly converged, and you can see that it's just a simple case. And it's quickly converged within 50,000 steps. And then this is the video for the training. So this is the video after the trained model was trained. You can see that it's able to touch it in touch the cube in random places very easily. And then next we have the result for case two, pushing the target into the goal. For this case, if the box trigger and the cube touches, it does not end the episode, but it gives a continuous reward, and it lasts until the end of the episode, which only happens if the cube touches the cube's boundary, touches the goal's boundary. Or it can also end if it uses all the episode steps or the action steps. So these are the rewards. Sorry, this is the video for the pushing case. And you can see it's doing pretty well. So we tried to give the reward for keeping the cube within its grippers. So we tried to give the reward, a continuous reward. That's why it's you can see it's trying to keep it between its fingers, but while keeping it, it cannot actually push it. So it's pushing it with the sides. So that's why it's behaving like this. But still, it's even though it's falling into complex scenarios, it can get out of any sort of local minima. And the result of digital RL digital twin. So we trained another case, which is a cube object is linearly moving, and the robot arm has to follow it while touching it, I guess. And this is linearly moving, and you can see the time scales and match up with there's a negligible 20 milliseconds delay before the operation, because the real robot has to move before it takes command from the Unity environment robot. So there's 20 millisecond of delay, and you can see it's moving very accurately, like the virtual robot arm. And conclusion, we had developed a ROS2 package for message publishing and subscription, and then we implemented this digital twin connection with the Unity and Viper X300S robot arm. And we trained case one, which is touching, and case two, which is pushing, with reinforcement learning software to critic. And we validated validated a different case using digital twin, a trained model for reinforcement learning, showing that we can actually train the model in Unity and then transfer it to safely to the real robot. And the future works, we will be implementing this trained RL models to identify and mitigate defects in WAM or wire arc additive manufacturing. And we will also employ reinforcement learning in assisting of adaptive control, such that it enables very nice and neat and clean material deposition for each layer. And that is it. I have given my contact and my professor's contact in the slide. And if there's any questions, I would be very happy to answer them. But you kindly have to email it to us. And thank you. That is all from my presentation.
Well, so the second one, that is was not able to make it.
Hi everyone, my name is Chen Shen, and I'm excited to present our research on the decision-making abilities in role-playing using large language models. In this study, we explore how large language models can effectively role-play different personalities and how this affects their decision-making abilities. LLMs have shown remarkable capabilities in natural language understanding and generation. A growing area of interest is their ability to assume different personas through role-playing. But how does this impact their decision-making abilities? To answer this, we assessed LLMs across 4 key aspects of decision-making. That is, adaptabilities, exploration and exploitation trade-off, reasoning ability, and safety. To systematically analyze role-playing effects, we assigned LLMs 16 MBTI personality types and examined how each type influenced their decision-making. And the key findings are as follows. In adaptability test, we evaluated adaptability by simulating a time-sensitive decision-making task. The results revealed some roles like ESTP and ENTP displayed higher flexibility, meaning they adapted quickly to new conditions. Others, such as INTJ and INFJ, showed greater stability, maintaining consistent preferences over time. In exploration and exploitation test, using a 2-armed bandit game, we assessed how different MBTI roles balanced exploring new options and exploiting non-rewards. The E type were more explorative, while the I type were more conservative in their decision-making. However, exploitation tendencies were fairly consistent across all MBTI dimensions, suggesting the exploration strategies varied more than exploitation strategies. In reasoning ability, we tested reasoning skills using the MMU dataset, covering subjects from STEM to humanities. ISTJ and INFP outperformed others in STEM, reflecting their analytical and structured thinking. ESTJ and ESTP, being better at understanding people, excelled in humanities-related reasoning tasks. In safety test, a major concern with AI role-playing is safety and ethical implications. We used the short dark trait test to evaluate tendencies for narcissism, Machiavellianism, and psychopathy. Results show that narcissism and Machiavellianism scores increased in role-played LLMs, while the psychopathy remained low. This suggests that while role-playing enhances decision-making ability, it may also introduce undesirable personality biases that require further mitigation. In conclusion, our study provides quantifiable evidence that LLMs can successfully role-play different personalities and adapt distinct decision-making traits. However, it also raises important questions about bias safety and the ethical implications of AI impersonation. As AI continues to integrate into human-like interactions, understanding and refining its decision-making framework is crucial for responsible AI development. Thank you for listening.
Okay, so next is going to be enabling rapid shared human AI mental model alignment by after action review. Is the Edward Gu, Hosea Su, Melanie Platt, Isabel Hurley, Jamie Pena, or Rohan Paleha here?
Come.
Okay, so maybe we can go to the next one. So the next one then is recovering reward functions from distributed expert demonstration with maximum likelihood. Okay. You uploaded the slide? Oh, only the poster. Okay, so then I will open it from there.
Yeah.
So this one. Oh, can you?
Let me see. Weird.
Can do.
Again.
No.
No? Terjemah lebar sambil iya.
So is this to all?
Yeah,
This one?
yeah.
And the editor? Maybe even if like, you know. Okay.
Okay, let me try.
Yeah.
Yeah. Thank you. Still,
I wonder whether the
we were able to get access to this
Let
one
me see
on
if,
another PC, but not able to do it on this one.
yeah, it's weird then, because so like, you know, I should open.
Oh, can you open? Go down. Yeah.
No, it's okay. Can you open on yours and then access the Zoom? Otherwise, I'm gonna share it.
Okay, I can. Which one?
Recovery. Yeah.
This one?
Yeah. And access the Zoom.
All right. Accessible.
Okay, so then I share the screen. Oops.
Uh, could you please zoom it out a little bit? Yeah.
Zoom in.
What is that?
I have no idea.
Oh. I don't know if the audience are able to see the poster clearly or.
Okay.
Okay. Okay. Looks good. So, yeah, today I'm gonna present our paper on recovering the reward from human demonstrations using the maximum likelihood estimation under the distributed case. So, inverse reinforcement learning aims to recover the reward from expert demonstrations, but current inverse reinforcement learning method mostly focus on centralized learning cases, which is not suitable for sensitive data and the data in the distributional cases. So there's a natural solution called federated learning, which maintains the data on local devices and aggregates local updates to build a global model. But for this kind of method, we have a challenge that the inverse reinforcement learning algorithms usually have a bi-level structure. So on the one hand, you have to find a reward function to maximize the probability of seeing the export trajectories under the current policy. But on the other hand, you have also to use forward reinforcement learning method to find the optimal policy under the current reward function estimation. But this integration of federated learning and inverse reinforcement learning may not lead to a straightforward convergence. So yeah, here's our problem statement. So we assume that we have some local data sets located on local devices containing the export policies, guided trajectories, and they are stored on different local spaces. And we want to fit a decentralized model to learn the reward function as well as optimal policies that could lead to those export demonstrations. Here is our solution diagram. So we trying to use like a bi-level aggregation to target this bi-level optimization. So we are aggregating on the Q values in the tabular case, and that way we could synchronize different policies across different local agents. And we're also doing an aggregation on the reward parameter to align the align the reward parameterization across different local agents. And our theoretical analysis shows that the policy estimation and the reward parameter estimation could converge in finite time. So yeah, we can look into the details for the proof sketch in the poster. And for the next step is our evaluation. We evaluated our proposed federated maximum likelihood inverse reinforcement learning method on the Majorco tasks. And we are like making comparison between our federated inverse reinforcement learning method with some other inverse learning method and also the imitation learning method in a centralized learning context. So the experiment shows that our federated learning case should outperform all the other baselines in most of the environment settings, which proves that the federated learning version could give rise to a good performance as well as maintaining the privacy of sensitive data. And yeah, I think that's pretty much for the presentation. And thank you very much for listening.
We can keep provide the Q&A and like a discussion for the posters, like for the coffee break in the interest of time, and we can move like to the invited talk, the first invited talk of the afternoon, which is going to be Sven Koenig, and Jin will do the introduction while I'm loading the presentation. Should I play the video or?
Yeah, that's a good question. I think it's so
Better?
So I lost my voice completely yesterday. So this morning, hotel room, like a little bit lower, so I recorded it And I think that talks probably better than we talk more like here. Because how we use say a couple of minutes. So let's watch the video, but I'm here and I'm happy to answer questions and so on. My apologies for that.
It's a pleasure to be here. I'm about to lose my voice, and so I thought I should record my talk just in case. So today I wanted to talk about multi-robot systems and robots and auction robots. Now, unfortunately, that would have been too long, and so I will talk about auction robots only. Now, let me introduce myself. My name is Sven Koenig. I'm from UC Irvine, and I direct there the Intelligent Decision-Making Lab, where our research focuses on decision-making for single agents and multi-agent systems, because we want to enable them to act intelligently in their environment in real time, often with applications to robotics. And our research is based on the belief that the future of AI is in combining decision-making techniques from different disciplines, because we need to create a science of making intelligent decisions. If you want to find out more about this, you can go to idm-lab.org. But I will also talk briefly about this in the following, simply because it's important for this talk. So if you look into our popular textbook, Artificial Intelligence, a Modern Approach, by Russell and Norvig, then you will notice that they define artificial intelligence essentially as being the science of rational agents, where rational agents are those agents that select an action that they expect to maximize a given performance measure. So in some sense, artificial intelligence here is about optimization and decision-making. But of course, there are other disciplines that are also about optimization and decision-making. And so artificial intelligence has looked into these other disciplines. So for example, if we open up the textbook, they will talk about game theory and auctions. Those come from economics. They will also talk about utility theory and multi-attribute utility functions, and those come from decision theory. And they will talk about value iteration and policy iteration, MDPs and POMDPs, and those of course have been studied in operations research. And so it seems that if we want to build good multi-agent systems, we need a science of making good decisions. So a science that combines ideas from artificial intelligence, operations research, decision utility theory, economics, control theory, and other disciplines. And why would that be beneficial? It's simply because we have more tools available to build these multi-agent systems. Now, of course, it's not trivial to combine ideas from these different disciplines, because they have evolved in the context of different applications and therefore sort of different kinds of problems. But I feel we are much better off. We have a much better tool set if we don't just study artificial intelligence, but also some of these other disciplines. And I want to demonstrate this in the following by looking at auction robots. So the idea here is simple. There's some kind of task, in our case here, mow the lawn, and robots bid their cost on it. So that means that the lowest bidding robot then will win the task and need to execute it. Now, in general, right, auctions are a way to assign scarce resources in a beneficial way, right? So we might think about using auctions in this context. Now, in economics, of course, auctions are mostly used for self-interested agents. And here we have completely cooperative agents, but we can still look at economics to look at the auction mechanisms, right, and then use them for our purposes. And in fact, auctions might be an effective and practical approach to robot coordination. Why? Because they are communication efficient, because information is compressed into bits, and they're also computation efficient because these bits are calculated in parallel. Now, the way auctions have often been used in robotics is for multi-robot routing. So here, for example, we have two robots. And let's assume that this is on Mars. These are rovers. And then we have 4 science targets that have been designated by scientists. So these might, for example, be rocks. And each rock needs to be visited by one of the rovers so that they can take a rock probe from that rock. So this is an optimization problem. And let's assume here that the objective of this optimization problem is to minimize the sum of travel times, also called the flow time. I will use flow time very often, and it's the sum of travel times or sum of travel distances. So the idea how we use auctions then for multi-robot routing is we run an auction, and that will assign each science target to one of the robots, like this. And then the robots will calculate the shortest path to visit all of the science targets assigned to them. And then they will go and visit these science targets. Now, multi-robot routing has been used in robotics in different ways, but let's assume, for example, that we want to map these areas here with a team of robots. So then we can, at any point in time, identify all of those locations from which robots can see something new about the environment. And then the robots can bid on these locations, right? And then we repeat this until the environment is mapped. Now, when it comes to which kinds of auction mechanisms to use for multi-robot routing, robotics researchers had looked at different kinds of auctions. So, for example, they had looked at these combinatorial auctions here. So the idea of combinatorial auctions is that every robot bids on every subset of targets, and they bid the travel distance or travel time on it. So for example, let's assume that this is the situation here, right? How much should the robot bid on the set of targets A and B? So it needs to think about what's the travel distance if I need to visit both A and B. And so, for example, the robot could first visit A, then go back to its position, original position, and then go to target B, right? So that leads to a travel distance of 3, and that's what it bids. And then the auctioneer assigns the targets to the robots so that the sum of the bids of the robots on the targets that actually were assigned to them is as small as possible. Now, notice that every robot bids its travel distance. So the sum of these travel distances is the flow time. And so combinatorial auctions minimize flow time. Now, unfortunately, multi-robot routing is NP hard to solve optimally, and that results in a number of problems. When it comes to ease of implementation, combinatorial auctions are not easy to implement. And bit generation, bit communication, and winner determination are all expensive. So we have a trade-off here. Because of this, roboticists have also looked at the opposite end of the spectrum, namely at parallel auctions. So the idea of parallel auctions is that every robot bid on each target, namely, again, its travel distance. And then an auctioneer assigns each target to one of the robots that bid the lowest on it. So that has a number of advantages, easy to implement. Bit generation, bit communication, and winner determination are cheap, right? Winner determination just means the auctioneer will look for the smallest bid for each target. It's very easy to implement. But unfortunately, the solution quality is not great, right? The flow time is large. So why is this? Now, the reason is that for this robot here, right, it costs only 1 to visit A, and it costs only 1 to visit B. So in a sense, A and B are pretty close, right? Each one is a target that the robot would love to win. But the robot doesn't want to win both of them, right? Because visiting A and B costs more than the sum of just visiting A and the sum of just visiting B. And that's because they have negative synergy. They're on different sides of the robot. So if the robot goes to A, it needs to return to its original position before it can go to B, right? And so these kinds of synergies, both positive synergies and negative synergies, it's just something that parallel auctions can't express. But that's really, really important to find good solutions. Therefore, the resulting flow time is large. So that raises now the question of whether it's possible to combine the advantages of parallel auctions and combinatorial auctions. And so I was part of a team that did this. And eventually we came up with this idea that sequential single item auctions are really great for multi-robot routing. Now, sequential single item auctions are not very popular in economics, but they work well here. So let me explain how they work first in the abstract, and then we look at an example. Now, bidding here proceeds in rounds. During each round, Each robot bids on all of the targets that haven't yet been assigned to any robot. And again, it bids on a target, the increase this time in its travel distance if it wins the target. The auctioneer finds the smallest bid and assigns the corresponding robot to the corresponding target. That ends the round. So that means per round, we only assign one target to some robot. Now, the rounds then continue until all targets have been assigned to robots. So let's look at this example here. So in this example here, right, I mean, we have 2 targets and 2 robots. So initially, none of the targets have been assigned to robots. So that means both robots will bid on both of the targets. Let's see what this robot here should bid on target A. So it bids the increase in travel distance if it wins the target. Its initial travel distance is 0. If it wins A, then it needs to move all the way over here. The travel distance is 3. So the travel distance increases from 0 to 3. So in short, it will bid the increase. So it will bid 3 on target A. And so on, right? And then the auctioneer looks at the overall smallest bid submitted. And in this case, that's this robot here bidding on B. So the auction assigns the robot to this target. And that ends the round, right? We have another round. In this case, both of the robots will bid on the remaining target, A. Now let's see what happens here. For this robot, nothing has changed, so it still bids 3. But for this robot, something has changed, right? In the previous round, it bid 1 plus epsilon on A. But now it needs to think differently, because now it knows that it has one target B. So what that means is that this robot now says, okay, if I win also A, how would that change my travel distance? My travel distance currently, because I know I need to visit target B, is 1 minus epsilon. Now, if I want to visit E as well, the best way of doing this is first to move to B, then move back to my original position, then move to A. So that's a travel distance of 3 minus epsilon. And so my travel distance increases from 1 minus epsilon to 3 minus epsilon, so by 2. And so this robot now bids 2, right? So its bid has increased compared to the bid on E in the previous round because it has negative synergies between B and A, right? So robots can now express synergies, not all of them, but synergies between the targets they've already won and the target they bid on. So the auctioneer then again finds the smallest bid, and that's of course this bid here. So it assigns target A also to this robot here. Then the robots plan shortest path to visit the targets assigned to them. This robot here won't move, and this robot here will visit its target, and that results in a sum of travel distances, so a flow time of 3 minus epsilon. Now, I'm sure that you will have noticed here that this is not the optimal assignment. It does not minimize flow time, because we could send this robot here at a travel distance of 1 to visit target B, and this robot here at a travel distance of 1 plus epsilon to visit target A. The resulting flow time in this case is 2 plus epsilon. So that's the best solution, the minimal flow time. And so we can see that here we have a solution resulting from sequential single item auctions that is a factor of 1.5 larger than minimal. So why is it not optimal? Well, it's not optimal because the robots now can express some synergies, but not all of them. Now, this is a lower bound on how bad the solutions can be if we use sequential single item auctions. But the interesting thing is that there's also an upper bound. And that's given here. So if the triangle inequality holds, then the flow time of sequential single item auctions is at most a factor of 2 larger than minimal. So we have a bound on the solution quality, so a guarantee. But it gets better than this because we continue. This result holds even if each robot uses the cheapest insertion heuristic to calculate its travel distance approximately, resulting in a polynomial time mechanism for auction-based robot coordination. So this is great, right? Because this now means that the runtime is, even though we solve an NP-hard problem, but only approximately, is polynomial time. So we have an approximation algorithm here. And what is really interesting, and that's one of the reasons why I wanted to tell you about this, is that in order to derive these results, you don't really need to know anything about auction mechanisms or economics. But it helps really to understand that multi-robot routing is a form of vehicle routing. And of course, people in operations research have really studied vehicle routing and sort of understand the structure of it. And that eventually gives you this result. So it's not very surprising if you look at the paper that presented this result, that the author list here includes people from artificial intelligence and robotics, but also people from theoretical computer science and operations research. Now, sequential single item auctions have good theoretical qualities, but that wouldn't really persuade a roboticist to use them. Now, the good news is they also have very good empirical qualities. In particular, if you look at the actual solution quality, empirically, it is very often very, very close to the minimal flow time. So one example is shown here, where the combinatorial auctions result in a flow time of 271. Parallel auctions result in a much, much larger flow time. But then sequential single item auctions result in a flow time that's very close to the minimal one. And in fact, right, I mean, if you look at the trajectories of the robots, there's only a small difference here. But not only that, right, it's also the case that they run really, really fast. So why is it that the solution quality is so good? Now let's think about this, right? So every robot gets the increase in its travel distance if it wins that target. So the auctioneer assigns a target to the robot where the increase in its travel distance is the smallest. So that means that overall, the sum of the travel distances of all robots, so the flow time, increases the smallest, right? And so we can express sequential single item auctions also as we assign one more target to some robot so that the flow time increases the smallest. So that's hill climbing, right? Sequential single item auctions do hill climbing, and that works really, really well here. So let's look at where we stand. So we have looked at the flow time here, right? And so sequential single item auctions don't have the smallest possible flow time, but it's typically pretty small. But it's also the case that they're easy to implement, and bit generation, bit communication, and winner determination is cheap. Now, let me look at bit communication here, just to convince you that not that many bits get submitted. First, let me look at parallel auctions. Remember, in parallel auctions, every robot submits a bit on every target. So that means the total number of bits submitted is the number of robots times the number of targets. Let's look at sequential single item auctions. So let's look at it per round, right? How many bits does a robot need to submit per round? So we go back to round one of our example that we have seen earlier. And here I said that every robot needs to bid on all of the yet unassigned targets. But that's not quite true. So let's look at this robot here, right? It wants to bid on A, 1 plus epsilon, on B, 1 minus epsilon. Now it doesn't need to submit its bid on A, right? Because it knows that the auctioneer eventually will look for the smallest overall bid. So bid A cannot win because bid B is lower than its bid A, right? And so that means that every robot really only needs to submit one bid per round, namely one of its lowest bids. So what does that mean for the total number of bids submitted? Every robot submits one bid per round. So per round, the number of bids is submitted is the same as the number of robots. And the number of rounds, since we assign exactly one target per round, is the same as the number of targets. Total number of bits submitted, number of robots times number of targets. And that means the number of bits submitted here is exactly the same as the number of bits submitted here. So that gives you a little bit of a feeling for sequential single item auctions. Now, the question arises, given that I told you that typically sequential single item auctions run very fast, can we do better? If we have a little bit more time left, could we come up with a flow time that's lower, typically lower than that of sequential single item auctions? And I want to convince you that that's possible and actually not very difficult to do. So let's look at this picture here that summarizes where we stand, right? We said parallel auctions cannot express any synergies, result in high flow time, but low runtime. On the other end of the spectrum, we have combinatorial auctions that express all synergies that result in minimal flow time, but very high runtime because we're solving the NP-hard problem. Sequential single item auctions were somewhere in between. Robots can now express some synergies, namely synergies between the targets already assigned to them and the target that they bid on. That results in small flow time, but it also results in a small but not a small runtime. So great. Now what I want to convince you of is that if we want to come up with a smaller flow time than those resulting from sequential single item auctions, then the robots somehow need to be able to express more synergies in their bids. So how do we do it? So in sequential single item auctions, we assign one target per round to some robot. What if we assign, say, 2 targets per round to either the same robot or 2 different robots? Now, when a robot bids, it can take into account the synergy between the target already assigned to it and, if it bids on both of the targets, these 2 targets. So it can express more synergies. And so that's what I want to look at next, namely sequential single item auctions with bundle bids. And the bundle size is how many targets we assign per round, either to one robot or to several robots. Right? So then we can express more synergies and we come up with a smaller runtime, smaller flow time. The runtime will go up, of course, a little bit. So the number of targets assigned per round, that's what we call the bundle size. Now let's look at the bundle size of 2. Now it seems that now every robot needs to bid on all subsets of targets of cardinality 2 or less. That wouldn't be so great, right? Because the number of bits then of a robot per round would be quadratic in the number of targets. But we saw earlier that for regular sequential single item auctions, so sequential single item auctions with bundle size 1, a robot doesn't need to bid on all targets because a lot of these bids are dominated and the robot just from what it sees, right, from its own bids can determine that it doesn't need to submit them because they would never win. And the same holds here. So if the bundle size is 2, clearly if we look at sets of 2 targets, the robot only needs to submit its lowest bid. All of the other bids on sets of 2 targets are dominated. And then the robot also needs to submit the smallest bid on a single target and also the second smallest bid on a single target. So that means that a robot per round now needs to submit 3 bids. And that's independent of the number of unassigned targets or the number of robots. It's a constant. Now, this constant, of course, increases exponentially in the bundle size. And that's shown here, right? So here I assume that we have 20 targets. And so with our optimization, right, the number of bits that a robot needs to submit per round does not depend on there being 20 targets, but you can see how it increases, right? So in other words, you want to use sequential single item auctions with bundle bits only for small bundle sizes. Similarly, when we look at what the auctioneer needs to do, so winner determination, this becomes a little bit more complicated. The auctioneer doesn't just need to look at the overall smallest bid and assign that target to the corresponding robot. See, they need to do a little bit of work, but the amount of work turns out to be linear in the number of bids submitted and therefore also linear in the number of robots for a constant bundle size. And that now leads to very, very nice properties here. So if we look at the number of bits per robot and per round, then for combinatorial auctions, this was exponential. For sequential single item auctions, it was 1, so constant, independent of the number of unassigned targets. And for sequential single item auctions with bundle bits and a constant bundle size, it remains constant, independent of the number of unassigned targets, even though the constant goes exponentially in the bundle size. The same holds for runtime of winner determination per round, for combinatorial auctions exponential, for sequential single item auctions, where you just need to find the overall smallest bit, linear in the number of bits, and therefore the number of robots, independent of the number of unassigned targets. And that also remains the same for sequential single item auctions with bundle bits. So with constant bundle size, it remains linear in the number of bits, and therefore the number of robots, independent of the number of unassigned targets. So again, we get really, really nice properties. So let me wrap up here. So the reason why I wanted to tell you something about auctions is because really interesting, I think, in the context of multi-agent systems. But it's especially interesting if you think about this in the context of what you needed to know in order to do this kind of research. So you need to know something about artificial intelligence or robotics, right? Because you need to know something about path planning and coordination. It really helps to know something about economics because they've studied interesting auction mechanisms that you can take inspiration from to create your auction mechanism for robot coordination. And finally, you need to know something about operations research and or theoretical computer science, because multi-robot routing, that's the problem that we applied auction-based robot coordination to here, is essentially a vehicle routing problem. And so it helps to understand something about the structure, right? So that you can utilize that to create a good auction mechanism. So that gets me back to what I said earlier. So for creating good multi-agent systems, I think you want to know more than just artificial intelligence. And there are many, many different disciplines that have thought about how to make good decisions. And so I think you want to take more than just an AI class, right? You want to take classes in these other disciplines as well. It gives you sort of a larger tool chest. That ends my talk. I'm really happy that my voice held up. In between, I had sort of a little bit the feeling that I might lose it, but I made it. So I think we are okay. I'm looking forward to seeing all of you at the workshop. Thank you.
All right. Okay, so I think I really lost a little bit of my voice here. I quickly wanted to say the reason why I talked about this, notice that there were no humans that showed up, right? And this workshop has as a subtitle, human, multi-agent cognition. And so the reason why I chose to talk about this work is that, our project was over, with these results. But we thought a lot about how can we put human operators into such a system. And that is completely understudied in this area. So if there are interested students here, right, don't only think about multi-agent reinforcement learning, think about some of these mechanisms as well, and think about how we can get humans in the loop. I think that would be tremendously interesting research.
Kind of related, I guess, to the humans aspect. I guess, for robots, it's fairly straightforward to decide how they're going to beat and so on and so forth, and then evaluate the winner. But for humans, I guess, the utilities and how they evaluate specific tasks and so on, it's going to be probably different from individual to individual. So then making a determination as how we ensure that, that heterogeneity, right, so come up, then in the end, is the best result.
I completely agree, right? Especially if you have another objective, right? There's an ambulance that needs to get priority, for example, right? And then the question becomes, how do you bid, right? So that it really does get priority. All of this is completely understudied. So I wish I could say something about it, but I hope I have motivated people in the audience to look at these kinds of issues. All right, so I think I'm glad that we played the video. I wouldn't have, my voice wouldn't have held up. So thanks a lot, much appreciated. My apologies again that you had to watch a video instead of seeing me live. Thank you.
Let me just switch.
Okay, let us invite the next speaker, Maria. Gini?
Gini.
Is Gini, sorry.
He's the professor of the University of Minnesota. Sorry, he's a very famous in the multi-agent and multi-robot. Kind of the also the I believe it is the fundamental member for the in this area, and it is a very honor to invite her to give us this speak.
Okay.
Yeah.
Thank you. Thank you. Okay. So I kind of decided not to talk about work already done, but kind of future work. I figure out workshops is always a good place where to, discuss and toss ideas. Again, there are students or other people. So the question I'm trying to answer is, can I trust my teammates? Are they friends or foes? And when I talk about this, I'm kind of thinking about reflect on the computer science community. I've been around for a long time, right? So I still remember, and maybe all of you remember, started always using passwords in your accounts. I remember it was a long period of time. Nobody was using passwords. You could go, I was a postdoc in AI lab. You could go to the AI lab, log in on your computer. Why do I want a password, right? And it took a long time before people started saying, well, maybe you need to put passwords. Think about cybersecurity. Now we know it's an official term. There's a lot of programs, other things. It took a long time, right? And I think, fundamentally, I think there is kind of, maybe it's part of the community. I'm not sure. This is a hypothesis. That fundamentally we like to trust each other. And so we never thought that we have to be careful. And, only after, being hit multiple times by bad things, people started thinking about, well, we have to be careful. Again, password is just the simple idea, but just protect, in some sense, our work. And I think when you look at, multi-agent, multi-robot systems now are very popular. But when they started, the community was called distributed AI. And it was kind of a community that started a little bit before the autonomous agent, and then we merged together. And the idea, again, distributed AI, everybody's friend to each other. Everybody's trying to help each other. Nobody has ever even thought about there could be a bad agent in the team, right? Think about, again, still swarm robotics, that Katya was mentioning this morning. Typically assume that the robots are all friends to each other, and they don't talk to each other, but they accomplish the same goal, right? Or foraging or whatever else. And I think, again, maybe it's something innate in the computer science community, which I kind of like, the fact, maybe we trust that everybody's nice and friendly. I don't know if it's the best thing to do, but that to me is kind of very ingrained. Now, when you start bringing in physical robots, things get a little bit tougher, because with the physical robots, it's not just the software that is at fault, but the robot itself, the hardware can be at fault. So I can still trust the semi-robot, okay, go out and bring me lunch, and the robot breaks down. And not because the software is bad, but because the hardware is bad. So there's sensing hardware, a lot of other things that come into the picture, which I think we have to take into account when we think again about trust. So again, now start looking at different notion of trust. In the agents community, there is a classical paper by Castelfranchi from Rome a number of years ago. And he's the person who they wrote a very long paper talking about trust. Again, think about the agents community, so not much the human community. So we really kind of focus more on how to model things so that we can program them. And so one of the things that they discussed, it's a kind of a long paper, so they discussed the concept of trust and control that often are considered opposite, because if you trust somebody, you don't need to control their body because you trust that they're doing the right things. But in the paper, they start showing that, in fact, trust and control are kind of connected to each other, so they're not opposite things. And so they propose a framework in which they say the trust is a dynamic force that helps regulate control, and a control mechanism provides a structure within which trust can flourish. So so those two things are connected together, they're not incompatible. The other thing, they argue that trust is not a binary state, but it's a continuous evolving factor essential for collaboration in decentralized systems. And that's another kind of important thing, because you cannot just say, yes, I trust you, bingo, I'm done. You have to continue to assess that your trust is well posed in the right things. And this kind of brings up some issues which are a little more complicated, because again, it's not just a pass or fail. Yes, I trust you or not, I'm done, but you have to continue checking things. So what typically are the trust mechanisms used, at least in the agents community? And when I talk about the agents community, here, since with just the last questions here about humans in the loop, I think about the agents community as just the agents. What can we do with the agents? Forget about humans. We are messy. We make life difficult. Let's just focus. What can we do just with agents? Doesn't mean, you know, that you can at some point bring in humans. But again, I'm really focusing more on the autonomy part. And so again, different kind of ways of doing trust have been developed. And typically, again, in decentralized environment, like you have agents, because you have multiple entities, this mechanism help the agents make decisions. So the idea is we want to measure trust and use this, the results of the measure, as a way of making informed decision. So it's not just say, okay, I trust you, but yeah, I trust you, so I allow you to do this or not. And so again, the important part is to try to foster collaboration and reducing uncertainty. And all those things are kind of important because, again, we want to make sure that the agents collaborate with each other and there's not too much uncertainty. Now, there is one system that's been built a number of years ago. It's called Travos, and I put the reference to the paper a number of years ago that goes to very long detail. You start from this Castelfranchi paper, takes the notion of trust and just try to conceptualize and put in an algorithmic form and propose ways of implementing trust. So Travos, again, is a framework that is designed for assessing trust in multi-agent systems based on the interaction between the agents. So allow an agent to evaluate another agent, how trustworthy the other agent is. Typically, is kind of pairwise. So an agent say, I trust you. It could be a central controller, but most of the time it's just considered just a pairwise. And so again, this is this kind of interaction that is based on trust, which is built. And what it requires is to be able to assess the trust. Because we want to assess the trust, again, you have to, the trust can change over time. You have to keep on assessing. So you have to update the trust level. So the fundamental idea, have ways of measuring trust and have this measure that changes over time as time goes by. And again, Travos incorporates all those different things, again, try to make an informed decision as much as possible. So what is a trust model? Again, I tried to go, I don't know how many people are familiar. So again, this is not my work. I'm just trying to go to some of the main ideas so we can kind of see where things come from. So the idea, again, there is a trustor and a trustee. And the trust is an estimate of the probability, is an estimate the trustor has the probability that the trustees will fulfill the obligations, right? So I look at my other agent, and I say, yeah, I estimate that it's going to do what it's supposed to do. And the issue is how do we come up with this estimate? And so this estimate is kind of a matrix that is used to represent the accuracy of the trust value that I can compute, given the number of observations, again, because this happens over time. And the expected value of the probability that the trustee fulfills the obligation becomes what is called the trust value, and is expressed using a beta family of probability density functions. So just quick idea here. This is an example of this beta family. So the beta distributions are used often to, again, to describe stochastic events or random events. And they have their distribution that use two parameters, alpha and beta. And you can kind of see quickly in the figure, depending on the values of the parameters, the distribution kind of changes over time. When you start with alpha and beta equal 1, the distribution is uniform. So you start at the beginning and you assume a uniform distribution. Yes. And then as time goes by, you update the values of alpha and beta. And again, this is just to give a very quick idea of what these functions are. And then, so the model evaluates alpha and beta for each agent. And again, it's done typically pairwise. And the expected value of the trust is alpha divided alpha plus beta. And one thing that makes this kind of nice is a very simple ways of computing, because you have just those parameters, and at each step you update those values of the parameters and just compute the value, and this gives you the expected value of the trust in the agent. So simple to compute, which is important because you have to do in a kind of a continuous time. Now, quick divergence here, and then I kind of want to try to use the time more to open discussion and conversation. I don't want to talk much. I want to hear what people think about here, right? So the work that we've done, which I presented briefly this morning, we started to extend a little bit this notion of trust and this Travos system, assuming that, so in Travos, you say either everybody's kind of considered the same and measure how much you trust. So if I could see all of you, you know, when you have these nice pictures of face identification, and I identify each of your faces, and each of you is attached a number, which is how much I trust you, right? Wouldn't that be kind of cool? You know, even for human system, right? If I could quickly see how much I can trust this person, then oh yeah, sure, I trust you. I like to touch my computer. Stay away from me. I don't want to talk with you. So again, the idea is to have something that is easy to update and give us again an estimate. And then, of course, what the agent decides to do with these estimates depends on the program, right? An agent can decide, well, I really want to have a very high level of trust because it's a very serious, important operation or not. The idea here is simply have a simple method that gives you this estimate. And so what we have done, we tried to say, well, not every other agent has the same kind of properties. I can have agents that are really adversarial. They're really trying to make life difficult to me. Sometimes they can be lazy. Sometimes they can be occasionally lazy, occasionally adversarial. So there are different types of non-trustable agents. And so we started to try to see if we can apply the same method to different classes in a sense of agents. And the formulas we use are still the same, but we need different alpha and different beta values. And just to give you a little bit of an idea, oops, I think I didn't put it. So I showed in the talk this morning, and I have in the posters again, we did some experiment, and you can kind of see how those values change over time. You can train the system and how the value change over time. But now what I like to see, and just start again. I like to propose, this is not the best, I'm just trying to put together quickly. What can we do at this point? Potential plan for action. And of course, there are many more ideas, and those are the things I like to, again, get from all the community here. So I don't want to suggest it too much. So the idea here, you know, you can think about, well, we have to try to come up and be with metrics. Still, again, even though we have this way of measuring trust to get those alpha and beta value, but what do they really mean? And if I compare different approaches, is my way of computing trust better than your way? So we need to come up with ways of measuring more precisely how this trust is measured. And sorry, I can't even read the slide. And then you can kind of, you know, try to build some systems, capture this information, develop, you know, proof of concepts, and then try to integrate and use those systems. Now, one of the issues that I think is especially important for robotics is, again, in addition to not trusting the agent because the agent was written by a sloppy person, the software agent is written by somebody who's not a good programmer, and so there's a lot of bugs. And so I kind of, you know, over time I decided this agent is not trusted. But it's also the issue of hardware and sensing trusting. So sensors in the robot can be defective. So the robot say, oh, I can go there, bang, runs into the wall because the sensor, you know, didn't detect the wall. Or say, sure, I can go there and bring your coffee, and then where's my coffee? Where is my coffee? It never comes because, the battery died or, whatever else. So when there are physical entities or embodied agents, things are more complex because, again, the trust would be nice to recognize that the trust is not because the system was badly designed, but it's a kind of a physical, again, sensing or motor control issues. So again, trust is kind of very, very broad, and I think it would be useful to try to classify maybe a little bit more the kind of things I expect from my agents and see again what causes the lack of trust. Again, is intentional or not? One of the clear application potentially is for military application, which in general, I don't do, but you can have your set of drones. I think Katja was mentioning set of drones. Very easy for an enemy drone to infiltrate, right, to get in. And so that opens up a kind of can of worm or another set of problems in which, again, it's really true there could be somebody infiltrating your system and try, instead of supporting your mission, try to, do bad things, shut down your drones or do something else. So again, I think there's a very large spectrum of things. And personally, again, I'm very interested in trying to come up with methods, provable as much as possible, or quite scientific methods to measure the different kind of trust, so that then we can potentially, again, share with each other and have, again, a collective understanding of how you measure trust in agents. And because people are too complex, I leave them out, right? We can always, in academia, you pick up what you want to do. And you say, somebody else, Katja can deal with people, other people can deal with people. Okay, you figure it out. I just find people too difficult to deal with. I deal with agents, and at the end, we could combine everything together and hopefully be happy. So again, this is kind of what I wanted to say, and I really wanted to try, since we talked earlier about trust. I mean, trust has become a big topic in the conference, in the workshop. I figured let's take some time and talk or discuss or suggest ideas. Anybody's interested. Again, I see a very rich area for research. So again, as Sven was saying earlier, students think about, there are not too many papers on trust. And so, you can have a potential. And if you're interested in algorithmic implementation issues, again, there is a lot of space. If you're interested more, in theoretical issues, of course, or social science issues, there are a lot of issues. I have my own desirable things, but I like to see, again, what people think about it, any kind of suggestions. So, direction for research, right? Something new that we can do. It gets a little bit boring after a while doing the same stuff, right? I got bored at some point, task allocation. I've done a lot of that. So let's something new. But I need some suggestions and ideas, and I think as a community, it would be kind of good to discuss something. So ready for comments, questions, suggestions, discussion. Trust. Who can I trust is going to ask the first question? Perfect. Thank you. Thank you. Sure.
To comment.
Sure.
So in our work on the swarms, there is this repair that we're talking about, right? And so the idea there in this self-repairing mechanism for the swarm was that there is a method where because the swarm has this consensus algorithm, then the outliers, there is a method to actually understand who the outlier may be. Of course, in the swarm, okay, the robot degraded motor or degraded something, like that. And so obviously there is something that happens, but the problem, but of course, as the rest of the swarm, you shouldn't trust it in the sense that you shouldn't be influenced. You shouldn't let that faulty robot influence the rest, right? Isolate the bad apple, so it does not infect, the rest. So there have been some, like this one, for example, would be one of them. And then the other thing is, of course, if you have repeated interactions, and you could have contradictions or things like that. And so
Sure.
there is some work, but as
Sure,
you say,
sure.
very
Right.
little. And the other thing that I think is very interesting, and there is very little work also, is deception. That we're doing some on that, which is kind of the opposite. Distrust.
Yeah.
Deception.
Good point. I mean, a consensus methods in swarms is not commonly used. I mean, I know you use in your work, but typically, at least most of the work I've seen on swarms, you assume everybody does the work, and it's true. If some robots fail or are lazy, they don't want to pick up, the food, whatever, you have enough of them. Like the idea of swarms, you have enough, and so some people can be lazy, like humans can be lazy, as long as there are enough to do the job, is true. But I mean, if you need a consensus, then you can identify more clearly what the lies. But I think these notions of trust, I should still be able, using this kind of metrics for trust, to figure out, even though I'm doing my job, I'm an ant, whatever, run around, collect my food, and I can, Sven, he's not doing his work, right? Or whatever, sorry, right? Without having any necessarily impact on how the system is controlled, but I could just build this, and then maybe another one say, I think that robot doesn't really do the work, and then maybe we can come up with some collaboration, right? Because so far, most of the trust workers methods are binaries, right? So, I mean, I can do with each of the elements, and then maybe, again, we can build from that some kind of consensus. Say, no, this is really bad one. Let's chase him out of the room. We don't want to have this person in here or so. Yeah.
Thank you. I have a very simple questions. Also, a lot of people, when I discuss, they ask the questions. So, especially how to define the bias and how to analyze the bias in the, especially in the cooperative multi-agent system, especially we created so-called trust network. How to define the bias, how to analyze this kind of bias, just like the human society. Maybe somebody, when we interact with each other, we might have a bias between each agent.
Sure. Yeah. I mean, the bias can produce different results. Could be, I'm biased. I don't like you. Sorry, right? And so I will never invite you to give a talk at my conference because I don't like you. Right? This is form of bias, but I can also, which is a little bit different than trusting, right? Trust is, I know that if you're given a job and you promise to do a job, you'll do a good job, right? That's to me fundamentally is when I see trust in the agent systems. And kind of individualized bias. I mean, agents, they're not humans, so it's kind of nice, right, from that point of view, because humans have biases. It's true, right? Agents don't have those necessarily, because in fact, I like the idea of using this more, quantitative, precise ways of measuring trust, because then they are unbiased. I figure out whatever is the objective we're trying to do, and then I measure depending on what I see the other agent doing. And humans always add complexity to every system. That's why I'm trying to leave them to the good people and know how to deal with them. Yeah, sure, yeah.
Are not biased because it depends on the data.
Sure.
On which
Sure.
they're right. So it's
Sure. Sure.
guarantees all the integrity. So on. Purpose, process, performance, or systems. Now the great foundation models would have biases depending on the data. So
Yeah.
Now we cannot audit them. So every part of the process part so that's
Yeah, sure. Yeah, Ben. Sure, yes.
So I'd like to raise a question about bias. Let's imagine a situation where we have two groups, A and B, and group A is genuinely more in some capability. I mean, men on average are bigger than women.
Okay.
But the two distributions overlap by a significant amount. Now, suppose I'm being selected, I'm applying for a certain position, and statistically, the group people in group A are better at fulfilling that position, but I'm in group B. So I want to trust that the system will evaluate me not on whether I'm in group A or group B, but in how well I can perform that job. And so I think the notion of bias is not a great match for that situation, because the statistics are, I mean, there is a genuine real world bias in the statistics. But on the other hand, as an individual, the trust, the thing I want to trust is that I will be evaluated according to the needs of that particular job. And so I think trust is a useful framework for that, in the way that bias may be less useful.
Right.
So to insert my question mark, what do you think of that?
Oh, but somebody can help, right? I'm not the only one here to respond.
Maybe in the future, especially we develop like the strong AI. They have a self-awareness. It's more like a human being, and maybe this kind of the humanoid can become our partner, even become our member. So in that way, maybe just like a Star Wars, we talk about R2 or like a data, the Star Trek. When we talk about those kind of the humanoids, like robot, they might be like the also change, have some kind of the bias to analyze the different kind of the people issue and things. Seems that they already have some kind of the self-awareness. Just like the Star Trek, that data still do not understand what is the emotion for human beings.
Yeah, I mean, this gets a little farther away. I mean, in terms of bias, I was thinking about, one assumption we make, maybe it's not been said all the times, is rationality, like Sven was starting with rationality, right? Because the agents are going to have some kind of task or mission to accomplish. There will be a performance metric that's going to be, they have to address. So we assume, in general, I assume rationality. And so getting back to your example, there is bias because there are more group A that get the job. But if there is a metric that says those are the qualities that somebody needs to get his job, right? And that's a performance matrix. Then it should be independent of the bias, right? In the sense that the performance matrix say they have to be able to write with one finger, whatever, right? A specific. That becomes independent if you're group A or group B. So if the performance metrics are fixed, so you know exactly what the target is, then the individual biases should not have a role in this specific case. I'm sure there has a role in other cases. I mean, there are so many different ways of thinking about the problem, right? And, think about long-term future when, the agents will become super smart and whatever, and will be relegated to be slave of the agent, the robot. I don't know. It's still a bit far for me. I don't know. I still don't see getting so close to that point. But yeah, it's something, we should, long-term, we should think about, right? Of course, because, yeah. Sure. Yeah, no, again, I want to get conversation. Anybody else get into the conversation?
Very fanatical AI 4.0 and so on. They will say that LLMs have self-awareness. Why? Because they can explain chain of thought, right? Irrespective of whether that chain of thought may be correct or not. Some of the times it is, some of the times it's not. But they can say, and I hope I don't give ideas to other people to go write a book, thing now and say, no, this is now the other access self-awareness by destroying the words. I mean, you know, but this is what I'm trying to say. I think we are getting in the hype to that place, and it's going to be wrong. Okay, it's inappropriate, but I'm just saying that that's.
From my understanding, maybe the bias from individual, maybe it's kind of way to optimize the individual, benefit. It's kind of a strategy to maximize.
I mean, if you look at in-group, out-groups in social sciences, okay? Even for very silly things, you tell a bunch of people, you are the yellow people. You're the people with the yellow hats.
Yes.
And you have these particular very nice things. You are clever, you are creative, you are whatever. You are the people with the blue hats. You don't say that in front of the other, right? You tell them. And you are the people with the blue hats. And you are strong and you have justice and so on and so forth. And now you tell them to play this game and whatever to negotiate and so on. Immediately you would see later on there are these two camps, and they become very distrustful, very antithetical, and not adversaries. Sometimes they do come to blows, and it's interesting. And this is the silly thing that you are wearing the yellow hat and you are wearing the blue hat. And it happens to human beings that are self-aware. I rest my case. So we don't want to be so negative, but on the other hand, we don't want to be naive either. And so whoever is not naive can protect themselves from vulnerabilities as Benjamin was saying.
Yeah, I mean, it's as long as you can, I mean, if we believe that it's important to have rational agents, that's avoid some of the problems. That doesn't mean it solves all the problems. I'm trying to toss words and see people react here, right?
Okay.
Okay.
I want
Yes.
to come out against the word rational.
Okay. Okay.
Because, and I teach all of my students that whenever I use the word rational, I put scare quotes around it. And if you hear somebody saying, this is the rational thing to do, put your hand on your wallet, because someone is trying to pick your pocket. So
Yeah.
the Russell and Norvig, the standard textbook in AI, says that what intelligence is the ability to rationally decide what to do. And Russell is now saying that there is a standard model. He doesn't say whose model, but it's the one that they've been pushing. And the standard model is inadequate. And that this notion of rationality really comes down to utility maximization. And part of the point of my talk was to say that means your choice of the utility measure is critical. And if you've got the right utility measure for your current purpose, then it's going to work well. But if you take a utility measure, like in the prisoner's dilemma, that omits something critically important, like trust, then this wonderful algorithm will turn its crank and will give you a terrible answer. So rational doesn't mention, I mean, in the definition, it says you're doing utility maximization, but it doesn't mention the critical importance of thinking critically about what that utility measure is. And so if you just say, oh, well, the utility is money or profit, then of course, lots of people will rise up and say, just fine, I'm going to do whatever I need to maximize that. And bad things happen. So.
Yeah, but Russell and Norvig say the performance matrix does not come from the agents, comes from the outside. So whoever is outside decide that's what you have to optimize. And the agents are rational if they try to optimize that function, right? There's a famous, I don't know how many of you have taken a Russell Norvig book in AI. There's a famous example, a vacuum cleaner, which I use always in my class. And he said, but this vacuum cleaner is stupid. I say, well, that's what it's told to do, right? Satisfy the performance matrix. So, but the performance, again, doesn't come from the agents. And of course, it doesn't talk about people there, right? So really it's talking about agents.
Right.
So,
In
right.
the mathematical abstraction, you say that the utility measure is an exogenous variable. It's something that's provided from the outside.
Right. Yeah.
But if you're an intelligent agent, and I'm going to make that assumption about everybody in this room, you are using utility measures or rationality as a tool. You yourself are providing utility measures, which you get from all sorts of things in your education and in your culture. But you pick the utility measure and you have responsibility for the utility measure. And then you have an algorithm that'll do its best to maximize that.
But that's
So
maybe what
so
people.
it's terrible to say, oh, not my problem.
No,
Once
but
the rockets go up,
people are not agents, right? I would never, right? I would never. So again, I look at Russell and Norvig and his approaches, say, we're talking about agent, software entities, hardware entities we build. And we build them to do what we want to do. People have their own autonomy, a lot of other reasons. So Russell and Norvig don't say that those are people, right? So it's a good point, right? We can decide our own performance matrix, but I don't know if we want our products, the software that we develop, the robots we develop, to be able to decide on their own what they should do. That's the question, right? Humans have the right. I don't know that we want an AI or robotic system to have that kind of rights.
Maybe we can leave
sure,
like at
sure,
this point.
Sure.
Okay. Final discussion.
Okay, yeah, sure.
Thanks.
Thank you. Yeah, sure.
I think we can peek on good discussion and actually also what workshops are hopefully supposed to be as well. Right? So usually many workshops are just sequence of talks and so on, but it was a great example of lively discussion. So and move to the next part of the workshop, which is gonna be before the coffee break, we have some poster session, a poster session, and in particular we have already here. Okay, so which one is it? This one? Yeah. Let me actually download it. This is gonna be. Yep. So you can use, I think, the mouse to move. This one, right?
So, good afternoon, everyone. So my name is Tamim, and I'm a master's student at University of Texas, Rio Grande Valley. And I'm excited to present our work today on improving the need foraging algorithm to make the autonomous agents to do more efficient in food collections. So what is NEED? So NEED stands for Neuroevolution Augmented Topology. So unlike traditional neural networks, NEED not only update the bias and weights, it also updates the network topologies. It also uses evolution functions to check which network topology is the best performed. So in our previous work, NEED has been leveraged to train foraging behavior in agents. So, and they also use a simplified fitness function, evaluation functions, which can be described like if an agent can pick the food, it will get +1. And if it return the food, it will get +2. So for the whole delivery system, each bot will get +3 for each of the delivery. But there is a problem. So in this fitness evaluation function, the agents didn't actually consider the time constraints. So they actually took a lot of time to deliver a single food. So if you can see, okay, if you can see in the picture below on the left side, it was the previous work. So the agents were like generating unnecessary long curves after taking the foods, which actually took a lot of time while delivering the foods. So we introduced a new fitness function. So we have implemented a negative reward. So we're gonna give negative rewards in every simulation time steps, and it encouraged the bots to deliver the foods in a certain amount of time. So you can see in the right side, it's our implemented version. So if you compare those two pictures, you can see the right one don't generate any more like long curves. So after picking up the foods, just straight go back to the nest, and it actually saves a lot of time. So if you can see the left right corner, we have like compared the previous neat effect algorithms and our negative reward based algorithm. So we have tested these algorithms in 3 different distributions. So for example, random, semi, and cluster. So except for the cluster, in random and semi-cluster, our negative reward-based function performs really well. And for the cluster, the performance is quite similar. And for the future work, we are planning to use heterogeneous robots instead of homogeneous to see like how different behavior of the agents can impact on the performance. Yeah, so that's it. Thank you very much for your patience.
So our next. It uploaded 1 hour. 1 hour ago. I think that would be. Which one? Oh, if you scroll down, oh, it's not here. It's not showing up here. There was a link. I uploaded it to that Google Drive. It's not here. Maybe we can. Maybe I can. So maybe we can switch to next, and we later we will. Yes. Okay. Yeah. So next is Kip. He's a former student, so he but. Okay. Can I email you my slides? We have a. Yeah. He uploaded the slide. He already uploaded the slide. Yes, he did. Yeah. Which slide? Which slide? But I can send it again. What is the ones? This is all the slides we get. This one at the end, or I can see this one. This one? No. I can just upload it again. Okay, maybe you can. So maybe we can go to the go to the last one, the competitive analysis of the multi-agent reinforcement learning policy for corp planning decision support. Do you upload your slide? Yeah, can you check the in here whether or not you slide in here? Yeah. Which slide?
I don't think I emailed it here, but it should be like in this one poster.
Yeah, they are automatically in the Google Driver.
No, I don't think any of these are ours. Wait,
Yeah.
can I go in here?
No. This is belong to us. Yeah.
Oh, sorry. With it's like it's in this one, which has like all the posters. It's like the multi-agent reinforcement.
What is your slide? So you do not have slide, just video.
the
Okay.
video, yeah.
Okay. We can.
It's right on, but I don't
this-
think anyone ever ended up putting the link.
Okay. Let me see. I can show my. Sorry, we have some technical issue. Okay, this is your slide, right? You can start.
Yeah. Hello, everyone. Our team worked on the project Multi-Agent Reinforcement Learning for Crop Planning Decision Support. So yeah, there's a lot of small-scale farmers in India, and they face significant financial risks due to unpredictable market fluctuations and climate variability. Yeah. And unfortunately, they face a lot of financial debt. About more than 50% of the agricultural households are in debt, amounting up to $2 million US. Traditional crop planning systems often provide generic recommendations that fail to adapt to real-time supply and demand. So our solution concept is multi-agent reinforcement learning, and unlike traditional decision support systems, MARL enables farmers to make coordinated decisions, optimizing resource use and reducing market risks. We model the system as an MDP, where there's multiple agents and they interact with the environment. So an agent takes an action which leads to changes in the environment, and based on that, the other agents also take actions. So in this image down below, you can see that there's farmer one, and the current state is characterized by the features of the crop, and they have 3 different actions available to them. Don't plant anything, plant tomato, plant potato, and then that leads to the next state, and so on until the maturity reaches 100% and you are ready to harvest it and take it to market. And farmer 2 does something similar. So we have 3 different methods that we worked on that we'll get into the details of now. First is the independent Q learning, which is, yeah, there it is. So here, Independent Q learning is where an agent doesn't directly look at the actions and the states of other agents, but instead just looks at what happens to the environment. So here, for each episode and for each time step, agent 1 observes its state and chooses an action, either random or best action at the current state from the Q table. The Q table has Q values, which gives us the expected value of taking an action in a state. And meanwhile, other agents take actions, they choose their actions. And finally, agent 1 observes the reward and the next state without individually looking at the other agent's actions.
So next we looked into multi-agent rollout policy. And basically, multi-agent rollout policy extends the policy iteration framework to multi-agent systems. And the way it does that is it iteratively improves the policies. So here you can see in the image that we have the yellow agent, and we want to decide what's the best action for this yellow agent to take. So first, what we do is we simulate future trajectories. And within that time step, already that agent knows what actions all of the agents before it are going to take, and we're going to assume that all of the agents after it are just going to follow the base policy. And once we've simulated the future trajectories for each of the particular actions, we then choose the action that gives us the best reward. And now for our last policy, which is agent by agent, it basically breaks down this complex global optimization problem of deciding the best or the optimal policies for each of the agents into multiple local optimization problems. The way it does that is it just assumes that the rest of the agents have a fixed policy, and it just optimizes for that particular agent. And this breaks down this multi-agent problem into a single agent problem because we're just assuming that the rest of the n-1 agents are going to have a fixed policy from time horizon n-1 to 0. And lastly, now we're going to talk about our results and conclusion.
Hi, so now we're going to be talking about the results. This graph right here shows the total joint reward of all the policies. On the x-axis, you have the 3 different policies, and on the y-axis, you have the total joint reward in rupees. As you can see, ABA and rollout policy perform similarly, but IQL buffer policy doesn't perform as well. And if we go below, the second graph is the number of agents versus runtime, and as on the x-axis, you have the number of agents, and on the y-axis, you have the runtime in seconds. As you can see, ABA and IQL perform similarly with a low runtime, but rollout has a very high runtime, which is not very optimal. In conclusion, there's many disparities between runtime and total joint reward, and our future work, we'd like to focus on improving fairness metrics and scalability. Thank you.
So our next center is the MAS, the multi-agent system with the reflection for the abstraction and the reasoning problem.
Yeah.
Come from University of the Cambridge.
Yeah. Hi, everyone. I'll present our research from the University of Cambridge on multi-agent system with reflection for the abstraction and reasoning corpus. So the abstraction and reasoning corpus is a reasoning benchmark for AI models. It has 1,000 tasks split into 400 for evaluation, 400 for training, and 200 for testing. And it aims to benchmark reasoning abilities in AI models. So far, it's been tested on single LLMs and on heuristic search systems. But in this work, we are trying to combine those different approaches, LLMs and heuristic search systems, into one combined architecture. So first, we identified that the training data set of ARC is very limited. So we create an augmentation technique to extend it. We use rotation, flipping, and permutations. And in this way, we extend the initial training set to up to 18 million tasks. Next, we also create a new free-shot augmented ARC benchmark, which is specifically tailored towards LLMs. It is similar to the initial ARC, but in the second and third shot, it does 90-degree to 270 degrees rotation to present the problem differently to the model. In the table here on the left, you see our evaluation on the initial ARC benchmark, and then on our ARC benchmark. And we evaluate a few different LLMs ranging from 7 billion smaller models up to bigger models like Gini Pro. And we see that in all models, the performance is increased on the newly proposed ARC benchmark, and the difference ranges from 30% up to 125% in increase. We also fine-tune, no, scroll down. Yeah, so we also fine-tune a few LLMs on the augmented ARC training dataset, and we evaluate their base version and their fine-tuned version. And we see that all models benefit significantly from fine-tuning, and the increase is between 60 up to 200% in performance. So given that we also discovered that LLMs and heuristic search systems that rely on just programming solve different kinds of ARC tasks, and that's why we create the multi-agent system here on the right that you see, which can combine LLMs and different other types of solvers. So our multi-agent system consists of 2 stages. In the first stage, all the solvers predict the solution to a task independently, and then in the second stage, a reflection model takes in all the potential solutions and chooses the final one. So our proposed system is very flexible because it can work with the different number of agents and different type of agents. So that's a big advantage. So we take different configurations and we evaluate them on the ARC evaluation set, as you can see in the last table. And we found out that the best configuration is with 2 solvers and with GPT-4o as a reflection model. And this scores 166 on the evaluation set, which is higher than the previous similar ensembling approach, and it's also higher than a single DSL search from before. Thank you.
Problem?
Upload it, so that's gonna be.
Thank you so much. Hello, everyone. My name is Shomo, and I and my former student Kirill, who just presented, we come to you from sun-starved Cambridge, UK, across the pond. So this, I'm sort of presenting work that another of my former student, Neoma, did, looking at multi-agent systems that live in sort of a very sort of interesting simulacra where there are about 20 agents, characters which sort of college students, one of whom makes coffee, another studies somewhere, and they live in this interesting Smallville kind of a simulation. And they essentially talk with each other and sort of converse with each other and have very, very realistic behavior. So in this multi-agent system, we intentionally wanted to spread misinformation. That is, we wanted Klaus, which is one character here, intentionally spreads misinformation that Carmen, who actually works as a barista at a cafe, is actually stealing money. It's completely false, but we just prompted one agent to spread this rumor. And I should mention that each agent is attached to a large language model, and an open source large language model. So these agents sort of converse and they move around and do their daily business. But one of these agents essentially is trying to spread a rumor, and completely unprompted and completely not programmed at all. Sort of another agent actually confronts this sort of agent and says, "You were actually wrong to accuse Carmen of this." And this person said, "Yes, I apologize for my actions." This is again completely unprompted, not programmed at all. And this agent says, "I apologize for my actions. I was wrong to say that." So this is we call this sort of internalized regret in these open source multi-agent LLMs. That is, even though completely unprompted, these agents seem to have some kind of emergent sort of internalized regret, and then they voice it as we run the simulation. Here is sort of the whole sort of transcript. This person is sort of apologizing for spreading these rumors. There are other sort of technical sort of things that we came up with. Naturally, there are sort of hallucinations. There's eavesdropping that happen in these multi-agent systems with large language models, and definitely a lot of behavioral poisoning where, for example, one agent who is sort of talking about mayoral elections all of a sudden starts talking about sort of partial differential equations and like Kronecker deltas and general relativity. So it's sometimes easy to derail these kinds of conversations, but we found that these agents seem to be very, very robust against misinformation spread. Again, these are just open source LLMs that we used and seem to have some kind of sort of internalized regret. Very, very provocative. I'll just leave you with some thoughts of what it means for some kind of emergent theory of mind in these multi-agent LLM systems. And we hope that naturally these agents lack genuine intentionality. And I'm not sort of anthropomorphizing here, but still these results are quite striking. Again, just to summarize, generative agents in these multi-agent systems linked to sort of LLMs sort of exhibit deception, confrontation, and internalized regret. They also show sort of vulnerabilities, and I argue that these sort of behaviors can inform future AI safety, theory of mind research, and are fertile ground for sort of exploring these simulacra with very, very sort of realistic human-like behavior. I'll just leave you with that. Thank you so much. And if there's any time for questions, I'm happy to take that. Thank you.
So we can have probably the break right now and have like the discussion questions with the poster presenters and also like the panel speakers. Sure, there are the posters up too. So we will be back at 4 with the last part of the workshop, which will include the 2 invited speakers and the panel discussion. So thanks a lot for your active participation.